Hello, this is Jason Kendall, and welcome to another one of my introductory astronomy lectures. Well, last time we talked about the nature of how light works, and we went back and further and talked about the nature of how the wave model of light was probably the predominant idea. And then we threatened to bring on Sir Isaac Newton. Well, let's see what he had to say. All right, in 1666, that's 110 years before the birth of the United States, 1666, he wasn't Sir Isaac Newton yet, Isaac Newton bought his first prism. And what he did is he was trying to determine what the nature of light was. He was extraordinarily curious about light. And so he bought his first prism and learned to grind lenses himself. But what he did is he wanted to disprove the wave theories of light. He firmly thought that the nature of light was that it was particles. And he called these particles corpuscles. It's a wonderful word, but the idea is that the light is constructed not of waves, but of corpuscles, of things going through. Why did he think that? Because with his experiments of light, he thought, well, let's see. Now, if you're going to bounce something off of a surface, if a thing bounces, like a ball bounces off of a surface, the angle of the incidence of the ball at the surface equals the angle of reflection, if the surface is perfectly smooth. So let's say we look at a mirror. You can take a beam of light from the sun, make a tiny hole in, say, a curtain that goes outside, and the beam of light goes through. Maybe there's some dust so you can see the beam, and then it hits the mirror. The mirror is a flat surface, and then it reflects off in a new direction. But the angle of incidence, meaning make the mirrors flat, think about a stick going straight down the middle to the mirror, as the angle that hits here is exactly the angle that leaves there with respect to the vertical angle. So just think of it as a plumb bob down to a flat surface of the mirror. And so the angles are always the same. Now what Newton posed is that this is what light does. Since light does that, and that's what particles do, so therefore light must be a particle. Otherwise it wouldn't have this property of reflection. So it also has the possibility of actually going in a ray. Since it actually goes in a ray, and we know that waves spread out on water, say waves just don't stay in a line, they actually spread out. So Newton said, well, it can't be a wave because I can make rays of light through curtains and make beams. I can do that. And it reflects like particles. So therefore it must be. Now, he did have to come up against the significant evidence that it has wave properties such as diffraction. But in any event, so he bought his prism his prisms and started playing around with them in 1666, and it took a long time, almost a decade, for him to actually come up with those ideas about it. In 1672, he was in the Royal Society, and he published his ideas, or at least promulgated his ideas about the corpuscular nature of light. And what he said is, he argued to the society this time after doing numerous experiments to try to determine this. He also argued for the existence of 7 different colors of the spectrum. In fact, that's where we get our Roy G. Biv from: red, orange, yellow, green, blue, indigo, and violet. He established 7 colors, even though there's a spectrum, even though there's not just 7 colors. But Newton was a mystic, and 7 was a mystical number, so linking light with mysticism was very Newtonian at the time. And so when Newton presented his ideas, he was attacked, well, by his old rival, Robert Hooke. So what did Newton present? Well, Newton said that because the prevailing idea of the wave theory of light could not readily explain the action of prisms or the actions of rays, everyone thought that prisms, or when you pass light through a material like glass, the glass corrupts the light, adds color to the light. And when it adds color to the light, it changes the light. So Newton said, but wait a second. So he took one prism, shone a beam of white light, sunlight, through it, and it spread it out into a rainbow. Then what he did is he took a second prism and put it to intercept the rainbow of the first prism. And if you angle it just right, what happens? Well, out comes white light. So the first prism breaks the light into a spectrum. The spectrum then travels a little bit till it meets the second prism. The second prism then recomposes the light back into white light. And so you get a beam of white light in, then a prism spectrum in the middle, and then a beam of white light coming out. And so Newton said, well, wait a second. Light can't be corrupted by the glass because out it comes. If it was corrupted, then it should spread even further. And also what Newton did is he took the two prisms and he actually offset one so that just the red part of the spectrum intercepted the glass of the second prism. And what passed through the second prism? Just red light. The red light was neither added to or destroyed. It simply was redirected by the second prism in a new direction. That's all it did. So Newton said, well, if it's corrupting, then the red light should have turned into blue or purple or green or what have you, but it didn't. It stayed red. So another argument for it is that Newton said, I know that the glass isn't corrupting it because, well, I can polish glass. And that's a very interesting statement. Because you can polish glass, you know it's not corrupted. All right, so what does he mean? When you take a piece of glass that's roughly made, there might be air bubbles in it, there might be sides on it. So what do? You take that and you grind it with sand or sandpaper or some sort of rough surface. And the rough surface then gets rid of all the big edges. And they use finer and finer and finer sanding agents and in order to get at smaller and smaller and smaller imperfections on the surface of the glass. So what happens is eventually you have a perfectly smooth glass, there are no imperfections, and the light becomes more and more and more clear. So the spectrum of light becomes more clear as you polish it, which means that you're getting rid of corruption in order to get what the people thought was corruption. So Newton thought the whole idea of the corruption of glass to be wrong, and that and in fact he is correct. He was correct about that. But when he presented all his ideas to the Royal Society in 1672, it was a huge debate, a huge hullabaloo, and Robert Hooke really attacked him for it because Robert Hooke really they just had a terrible rivalry. And Robert Hooke advocated the wave theory of light based on refraction and diffraction, and it wasn't a settled matter. And as a result of the public nature of this battle, Newton stopped talking about it, stopped engaging in the debate about light for a very long time. Well, so about 6 years later, Christian Huygens set out to disprove Newton's idea about the corpuscular theory of light. And he did so by trying to incorporate the nature of refraction and reflection into a wave theory of light. And that was very difficult for him, but he managed to do it in some ways. So he advocated the wave theory, and light was acting as a wave, but he ran up against some problems. And one of the problems was, it had been known for a long time, since about the time that Newton got his first prism, that there are certain kinds of rocks, calcite crystals specifically, that were clear. They were crystal clear. However, when you looked at them, they made multiple images. So the crystal itself, it seemed to be clear. When you passed something through it, passed light through it, or you just looked at an image through it, there'd be multiple images that would occur. Nobody could really understand what this was going on, but so these calcite crystals would make them. And even weirder is that if you took one calcite crystal and put it on top of another calcite crystal and looked through that, there'd be nothing. It'd block the light. So they didn't really understand what that was at all. And Huygens' idea about how how waves propagate through materials was not well understood. And so basically, Huygens originally thought, well, they've got to be different kinds of light. Maybe some are circular, spherical waves, and some are ellipsoidal waves, and you add them together, that might make the calcite. But that really didn't help at all. The ideas about why these crystals worked this way was not well understood, even though their phenomenology was well established. All right, so 1703, wow, a whole long time after that, Hooke dies. And when Robert Hooke dies, Newton is actually a little bit glad, 1704, he publishes his Optics, which is his great volume of work about how to do all of the experiments that he described back in 1672. He described exactly how to do them so people could more easily replicate them and prove the corpuscular theory of light. Well, Newton truly advocated this corpuscular theory, and because of his success with the laws of motion, because of his success with Principia, because of the success with gravity, his ideas carried enormous weight. And so people thought that the optics was the correct way, and that the corpuscular theory held the day for a very, very long time. So how did Newton approach the idea about the crystals? Well, he said, well, light, maybe since they're corpuscles, they might have sides. They might have a left side, a back side, a front side, and these sides might be different. And so the different sides then allow you to bounce differently inside a crystal. So it was his argument, and well, that's how he explained it. It wasn't a very good argument, but it's fascinating. He thought about the concept of sides. All right, so when we look at the nature of what he was talking about in 16, we find that his Optics was an extremely large influence on scientific thought, and even well after he died. He died in 1727, and his work continued on. We still use his laws of motion. We talked about them before. We still use his law of gravitation. We talked about that before as well. But we don't use his corpuscular theory of light anymore. So there was many more advances to occur in order for us to understand what this nature of light is. And part of the reason I'm kind of going through this historical aspect of things is because sometimes when we look at an introductory level textbook or something, it'll just tell you what was done. It doesn't describe the battles that people had. There were interpersonal battles between Newton and Hooke, and the ideas relied on experiments which couldn't necessarily be done by them very easily at the time. And these were new ideas. In fact, when Newton started working with prisms, they were new toys, and so people didn't think they were really valid scientific instruments for a long time, or couldn't even make them so you could regulate them because there was no theory about why they worked, so how can you use them scientifically? So as knowledge dawns, as knowledge grows, it's important to know where it comes from, because it comes out of human interactions. It comes out of people working together or against each other to try to get ideas out there. And one person says, well, I don't think that's right. And where Christian Huygens thought that Newton was wrong, he wasn't really mean about it. He just didn't agree. So Hooke was really mean about it, though, and he attacked Newton. So all these interesting interpersonal relations that occurred through the history of science. And that's what we should expect, actually, when we look at anything done by people. So next time, we'll see how Newton's corpuscular theory finally was dethroned. All right, we'll see you next time.